Whatever.
Here. Okay. Yeah, I just wrote it. Oh. It's a curse, trust me. I'm like, I wanted a question right at the beginning. I went, oh my gosh, there is a one. I wrote it.
Well, I put 20 in. I went up 40 back. But I'll tell you around. I got up to 80 something. She loves her.
So y'all do the front row.
I don't know.
She put the whole time on the way.
What? Oh, like if they're all sick? I don't know. All right, if nothing else, take a stab in the dark.
Takes it away.
All right, so that's 16, isn't it? Woohoo! Can I cry now?
Sure.
Okay, so what happens after the first step? All right, so I'm going to go up here. I'm going to write up here what you get after the first step. After step 1, you get pH, CH2. That's your clue. Okay, now what are we adding? D2O. What does that do to a Grignard? How quickly we forget. Oh, that arrow is like horrible. It's this thing. It's off again. Okay. Yeah, somebody got it. There was one. My button is broken on my shirt. It's like only half a button there. Okay. Is it all coming back to you now? Okay. Remember that this carbon on the Grignard is negative. Okay. Nucleophilic / basic. Okay. And what you're doing is you're protonating it with the D2O. If you threw water in there instead of D2O, you would get that. Okay, how do you get an alcohol from a Grignard? What kind of compound do you have to add? A carbonyl compound, right? And then you protonate it. So if you took this and you added this, what would you get? Okay, and then you protonate that, and you get a alcohol, N-alcohol, I guess I should say. Okay, you got to remember how Grignards react. Okay, I told you it was my favorite reaction. All right, now look at this one. I have two favorite reactions. That's one. This one. What is the major organic product for the reaction below? So we've got what kind of compound? Freaking bug me. This is an. Can you tell me what kind? Okay, that's a good start. Okay, and what are we adding? HBr, an acid. I agree. Okay, so what are you gonna get? What you think? Okay, let's do the mechanism then. Maybe that will help. Okay, so what does an acid do? We've been talking about this. What do acids do? They donate what? Bromine? What are they doing? Hydrogens. Okay, so we've got HBr. I will put the lone pairs in for you. Okay, there's my lone pairs. Okay, so now what does it do? We're going to go from the O and we're going to do what? Reach out and grab the proton. And what happens to the electrons in the HBr? They go to the Br. All right, so what do we have at this point? I guess I'll do like this. Okay, so here's what didn't change. What changed? We made a bond from the O to the H, right? Okay, and this lone pair is still there. It should have been green. Just keep my colors. All right, what do I have now? Oh, what? What am I missing in this little picture? Something that y'all like to skip. A what? Oh, positive. A charge. Okay. And then what happened to the bromine part? What did I get? Okay. Then what happens, you think? Water leaves. Awesome. Okay. So how do I draw the arrow to show the water leaving? From the bond to the O. Okay. So what do I have now? I have my little structure. I really don't want to touch this yet. Okay, here's what didn't change. Agree? Okay, so when I took those electrons and put them on the O, what do I get? Water. The O has all 8 of its electrons, so it's happy. Okay, what else do I get? Yeah, what is that called? A carbocation. Okay, now what do you want to do? Rearrange. Why doesn't the bromine just go there? It's secondary and we can make it tertiary. How are we going to do that? What are we going to do? What's going to move? The hydride is going to move. If the H moves and takes its pair of electrons with it. All right, so now I have I wrote it a little different. That H is now there, okay? And what is this carbon? Okay, so we went from a secondary carbocation to a tertiary carbocation, okay? Now, that is occurring within the molecule. Reactions that occur within the molecule or steps are easier than those that occur between two things because those two things have to find each other and get lined up, okay? So, the last step is going to be the bromide going to the carbocation. Okay, so what I want you to remember, okay, be that way, is that whenever a carbocation is the intermediate, you can get rearrangements. So don't forget to look for them, okay? So yeah, that means you had to know that the carbocation was for it. All right, so here's your final product. Okay. Starlight. Okay. They all coming back to you now? Okay. There are other methods for converting alcohols into alkyl halides that don't involve using HCl or HBr. Okay. The first one is using a phosphorus trihalide and pyridine. That's PCl3 or PBr3. Okay, have you heard of them? Phosphorus trichloride or phosphorus tribromide. You might have had to like name it or something in general chem. So PCl3, if you use PCl3, what will that put on in place of the alcohol? What halogen you think? It is not a trick question. What? Chlorine. Okay. If you use PBr3, what are you going to put on? Bromine. Okay. So pick the one for what you want. Okay. All right. Over here, it says or P and I2. So what does this little thing say? If you take phosphorus and iodine, you put them together, it makes PI3 in situ. PI3 isn't real stable. It's hard to keep. So typically, put all that together, it makes PI3, and you throw your alcohol in, and boom, what do you put on? An I. Okay, so why does this is so nifty? Well, phosphorus and oxygen end up combining together, and PO bonds are extremely strong, okay? And that makes a leaving group that you can easily displace with your halide. Okay, so you can readily convert alcohols into the corresponding alkyl halides. What's really nifty is that there's no rearrangements. Big plus. Okay, so if you had started with that compound that I showed you on the other slide, this one, and you wanted to make this one. All right, I'm going to go with this because I'm trying to get it to fit. I'm afraid I'll go too low. Okay, so if you wanted to do that, what would you use? PBr3. Okay. Now, typically, they will sometimes put pyridine in there. Pyridine is this. This helps in case any of the acid gets formed. This will immediately react with the acid, okay, because it's a base. It acts as a base. All right, now there's one other way that you can do the chlorine one. Thionyl chloride and pyridine also works. Thionyl chloride is SOCl2. It looks like this, SOCl2, okay? And it works similarly. You end up getting SO2 gas given off. Which stinks, by the way. This is not a fun one to use because it's smelly. You have to keep everything in the hood. Okie dokie. I think that this was supposed to be on top of that. Somehow I missed fixing that. Look at that. Wow. If I wanted to do that, it wouldn't have worked. All right, so if I do that there. Voila. Okay, everybody got that? So the big deal is no rearrangements. So if you want to make something, you want to make sure it makes the alkyl halide that you want. Use this method so you don't get any rearrangements. I mean, if it's tertiary, you could do it either way. Okay, so here's some examples. You probably don't have this slide because I made it up the other day. Okay, so what do you get from that top one? What's going to be your product? Yep, you're going to put a BR where the OH is. Oh, let's go though. Okay. So draw everything just the same except where the OH is. We're going to put a bromine. Okay. What about the next one? What do you think? Put a Cl. where the OH is. Okay, what if you did it this way? What would happen? What would you get? Whoops. There we go. Here is your clue. Yeah. So what do you think will probably move? A methyl. Okay, so what am I going to get? What do I have on this carbon? One methyl. What do I have on this carbon? The other methyl. Okay, remember that there is a hydrogen there. Remember, when you're messing with sticks, if you forget about where hydrogens are, draw them in. Okay, where is the chlorine?
The first one.
Yeah. Okay, so you see the difference. Okay, how about that bottom one? And it'll usually say P, comma, I2. Just like that. That's usually how it's written. All right, so here is your clue. Isn't that nice? What am I going to do? Okay, replace the alcohol. Look, it's still off with a iodine. What about that methyl? It's still there, right? Okay, you probably drew it much nicer. All right, anybody have questions on those? You could also use thionyl chloride here too. Okay. What is the major organic product for the reaction below? Now you're going to have to figure out the name because I didn't draw the pictures. Can you read it getting there? They make the structure so light when I paste them over, and y'all, they are not that light when I do it. That help? I don't know. I draw the picture and then they basically what you want to do. I did open that, didn't I?
Yeah.
Okay. I don't remember doing it. It's too cold out. Can I call in cold and tired? All right. All right. Are we all up here? I had 16. Now I have 17. All right. Yeah, it's B. Woohoo. All right. So you made up for the last one. Okay. Okay. Ethers are alcohols that instead of having an H there, they have another R. So their reactivity is very different than alcohols because they don't have that. Okay. OH minus and OR minus are strong bases and are poor leaving group. I'm all choked up. They have to be activated before they can undergo substitution or elimination. And I think I mentioned that already. We're going to show you how to make this little thing. It's called a sulfonate ester. It's a weakly basic leaving group and it easily undergoes substitution. Okay, it gets used quite a bit. So basically we take an alcohol and we add sulfonyl chloride. See what it looks like? You have an R group, and then you have a sulfur with double bonded to two O's, okay? And then you have a chlorine over here, okay? It's a simple substitution reaction, nothing fancy, okay? And you end up getting this. This is your sulfonate ester. Okay, remember an ester is O-carbonyl R. That's a regular ester. This is a sulfonate ester. So you have O and you have that sulfur thing. And then you have whatever R group is on the S. There's a variety of R groups that can be used on the sulfur. I'll show you those too. All right. Then typically they do it in pyridine. Remember, pyridine is this. Okay. And then it will easily get protonated. Okay. And so the chloride would be the counter ion. Okay. And you can easily get rid of that in your sulfur stuff. Okay. So you see what we're doing? That's all we're doing. We're substituting for the chlorine, and then the pyridine is removing the proton. Okay, the pyridine is a better base than the original alcohol. And since it's in there, it will remove the proton. That way you can add this 1-to-1. You don't have to worry about the alcohol getting protonated and messing life up. Okay, so now, why are these things such good leaving groups, and what do we do with them? Okay, first of all, this is the main one that gets used. It's para-toluene sulfonyl chloride. It is often abbreviated TSCl. You will see that in journal articles and things. Okay, this is the simplest one. It's methane sulfonyl chloride. It works too. Not as nicely as the other ones, but it works. And trifluoromethane sulfonyl chloride. So you see the difference? That one has 3 fluorines. That is often called a triflate. I don't know why they came up with all that, but they did. Okay, so redraw the structure below without the TS shorthand. So what are we going to have here? We're going to have our 5-membered ring. And we're going to have the carbon is attached to the O. Okay, and then what do we have? It's attached to the O. Remember what TS stands for. Okay, so what do you think I'm going to have from that down there? What? Sulfur. And what's it going to have on it? 2 double bonded O's. And then what else? A what? The benzene ring. Wow. Okay, and then what's over here? CH3. Okay. Now, how do you make that? What do you think you start with to make that? Because we don't buy that. We make it. There's your clue. What are we going to start with? What kind of compound? We'll look on the last slide. What was it? What was ROH? An alcohol, right? So we're going to have that alcohol, and our reagents are going to be TSCl and pyridine. A lot of times they write it. Sometimes they write PYR as a shorthand for pyridine. You might run into that too. Okay, but it wouldn't surprise me if you run into this TSCl on the homework on this app. Okay, let's put it this way. I hope you run into it in the homework. Okay, everybody got that? So if it was the methane one, instead of the benzene ring over here, you'd have a CH3. Instead of, if it was the trifluoromethane one, instead of the benzene ring methyl over here, you'd have a CF. Okay, so you see how it works?
How did you know it was that?
Because it said TS right there. I asked you to redraw the structure below without the TS shorthand. TS is shorthand for this one. Para-toluene sulfonyl chloride is abbreviated using TSCl.
But it's not, it's just TS.
Right. You use the TS to make, the TSCl is used to make that. TS is the para-toluene sulfonyl part.
Okay.
Okay, does that not make sense? This is TS. Okay, and it's really commonly used, like all the time people use that. because it's a really easy way to make your alcohols into good leaving groups. Because remember, OH minus, is that a good leaving group? No, it's rotten, crummy, lousy, awful, because it's a strong base. We want weak bases. Okay, so what do we do with these? We take nucleophiles and we add them to them. Okay, you cannot take CH3S minus, that methyl sulfide nucleophile, and add it to an alcohol and get the product that you get from this. You have to make the alcohol into a good leaving group. Okay, so here is our leaving group. Notice where the O from the original alcohol ends up. It ends up in your leaving group. Okay, here is the cyanide nucleophile. All you're doing is substituting on the CH2 for the ROTS. Okay, what kind of mechanism is this little pill that I have up here? Yep. Okay, so here is what your leaving group is. I'm going to try to get it all to be on here reasonably. Me and the pen are not one. All right, so here, I'll put all my lone pairs. Okay, so now this negative charge, you see, is stabilized by resonance. Okay, so if I take the negative charge, start at high electron density, if I push that in, what do I have to do? Push out to the O, and it doesn't matter if you pick the top one or the bottom one. Okay, it's going to do both of them, right? Okay, so what, remember, resonance arrow. So what do I have? I'll draw what didn't change. We didn't mess with the top double bond O, did we? We didn't mess with that benzene ring, did we? Praise the Lord, we haven't messed with them yet. Okay, so now, what do I have? Well, I only took one lone pair and I pushed it in, right? So the other two lone pairs are still there. And then between the O and the S, we have a double bond. What happened to the O on the bottom? The double bond is now gone, and we got an extra lone pair on there. All right, I'll make it big. Okay, did we do anything to the lone pairs on the top? No, they're still here, right? Even though you can't see them very well. There we go. Okay, so draw the other red. Oh, and what else do we need? What's the net charge over here? So what do I need over here? Where is it? On the bottom of it. Okay, now draw the next resonance form. Where do we start? At the O what? At the minus, right? And if we go here, then what do I have to do? Go where? Yeah, which one? The other one, the one that we haven't touched yet. Okay? Because if we do the one on the left, we'll just go back to that. Okay? So draw what didn't change. Okay, so I didn't touch this double bond O, right? I didn't touch the benzene ring or the methyl. Okay. Down here, what do I have? A double bond, and up here I'm going to have an O with 3 lone pairs. All right, let me get in the blue color. I'll make a match. There we go. So this O up here now has a negative charge. Okay. These electrons didn't get to party. They stayed home and studied like good little students. Okay. Okay, so you see how all 3 of the O's are stabilizing the negative charge. That's why it's a weak base. That's why it's a good leaving group. Okay, and no matter what you have over here, it's all the same. So if it was CH3, instead of the benzene ring with the CH3, it would be the same thing. If it was CF3, it'd be the same thing. Okay, that's why we like tosyl groups. Okay, here are the 3 leaving groups. Okay, with the different things on them. So you see how you can stabilize every one of these. Doesn't matter if you go up or down first, just start at the negative. Okay, see how they're all stabilized throughout all 3 of the O's. Okay, it all works the same. All it changed was the R group on the sulfonyl. Which one do you use? Sometimes they did studies and they would use different R groups just to see if it made a difference, like if they're checking the rate of the reaction or something like that. Okay, I don't think you're going to do any of those in lab. Okay, so do you remember how to dehydrate an alcohol? We did that a little while ago. We're going to use H2SO4. That would be this one, right? Or phosphoric acid. What's that? H3PO4. Okay, and heat, and you make the more highly substituted double bond. Remember all that? Okay, so what happens? The OH gets protonated. Then what? Water leaves, and then you pull off a proton and make a double. Okay, what kind of mechanism was it? There's your clue. What? Because you go through the carbocation. Okay, so what do you get for this one? Who do you think is going to be your product? A little practice. What you thinking? Not hearing much. I don't see much smoke. What do you think? The OH is going to come off. Okay, so how do you draw it? Do they have a problem with that? What? Yeah, it's going to rearrange. This has how many bonds to that carbon? I'm only written wrong answer. Okay? Make sure you check. And if you draw it with sticks, make sure you know where the hydrogens are. So who's going to move? Who's going to rearrange? A methyl. Okay, so what are we going to get? Okay. Holy moly. Okay. What happened to this H? Whoops. Wow. What happened to this H right there? All right, the OH gets protonated, water leaves, and you form a carbocation. Then what happens? I'll draw that carbocation. Okay, what kind of carbocation is that? Secondary. So we arrange to become more stable, or tertiary. Okay, so now what are we going to do? How do we do the rearranging part? What moves? One of the methyls moves. Remember, it brings its electrons with it. Okay, so the carbon that's left behind becomes, I'll get out of the way in a second. can draw what didn't change. Okay, so when that moves over, this CH now has a methyl on it, right? And this carbon becomes positive. Are you positive? Okay, now what's the difference between that and that? Got the methyl in the right place. What else do we got to do? Make a double bond. And how do we do that? We're going to take this H and we're going to pull it off. What pulls it off? The water. So we're going to pull off that H, that proton, and those electrons go down there to make the double bond. Okie dokie. Okay, now that we reviewed that, what do you think we get in the bottom one?
Okay, so I have a question before we pass it. So you know how when we were getting our test back, you were talking about how I was doing before doing this thing where it was in acid and they were trying to deprotonate with water, but water wasn't basic enough to deprotonate.
No, they weren't deprotonating. They were protonating.
Okay.
Yeah, here you're going to have, oh, I did it again. You're going to have H3O plus in there. That is what protonates this, not the water. The water can deprotonate this because of the plus charge. That makes it a strong enough base to do that, okay? No, good question. All right, now, what do you think happens down here? What? We're going to make it 5.
Wow.
Oh my gosh. Because 4-membered rings are highly strained, right? What is this angle in here? All right, hang on. I know better. I'm not going to do that again. Okay, what is this angle in here? What's the angle in a square? Are you sure? Okay. What does it want to be? What does that angle want to be? It wants to be what? What is the hybridization of that carbon? SP who? It's not SP2, it's SP3. So it wants to be 109.5. So it wants to open, okay? It doesn't want to stay closed. So what happens is this is going to react with our H3O plus, just like we did up there, okay? All right, and then the water leaves. Can I skip that step, or should I write it down? Yeah, that's what I'm doing. All right, I'll write it out. All right, so we're going to get I don't know that it's going to look very good. Okay, that. Okay, I tell you what, I'll write in the, like it is up there. Can you see that? Yeah, all right, I'll switch. There we go, you can see this. Did something just change to my left? It's okay, there it is. Okay, and then what do we lose? Water. How do we draw that arrow? The bluest dark. The electrons go to the O. Okay, so now here's the big deal. Where are we now? Okay, so we have H2O. All right, so what does this carbon have on it? A positive. Okay, now what happens? Look where we want to end up. So what's going to move? Let me try to get this bond looking a little better. Okay, so what's going to happen is one of these, it doesn't matter which one, it's symmetrical, right? We're not going to unsymmetrical ones. Okay, this is going to go to there. So it's going to leave here and it's going over there. It's going to leave here and it's going over here. So which carbon is going to become positive? One that it was originally attached to. Okay, so you're going to have, I'm going to draw it goofy. Well, then again, on this board, everything looks goofy today. Poor little thing. Okay, so it was attached to this carbon here. Now it's going to go this carbon, and this one is going to be positive. Okay, it was here, and now it moved over. So this carbon here becomes positive, the one where it was attached to. Okay, this is not a minus, this is a bond. Sigh. Okay, now remember that this carbon here, what does it have bonded to it? It has a carbon, and a hydrogen, okay? So there is a hydrogen on there, okay? But is that the one we take? I take the other one, okay? Because this one will make the more highly substituted double bond, and that doesn't even look right. Oh, God. Me and this thing. I'm telling you, it's like off. All right. How's that? Is that better? Okay, so now this is the H that we're going to pull off. So our water will pull up that proton, and then those electrons will go there. Okay, so you regenerate your acid. That's why it's called acid catalyzed. Okay, so if you need to, sit down with a piece of paper and draw it out nice. And if you want to come show it to me and make sure you got it, feel free. Because, oh my gosh. Okay, a milder method involves using POCl3. Okay, POCl3 looks like this. Remember that phosphorus, I didn't mention this earlier, that phosphorus and sulfur, they break the octet rule. Yeah, so you just have to let them have all the bonds they want. Make everybody else be right. And let them have all the bonds. Okay, PYR is what? Pyridine. You're going to get that pyridinium chloride salt again. Okay, so when you do this, P and O make really stable bonds, so you don't get any rearrangements. Okay, so notice where we made our double bond. Okay, so if you don't want to rearrange to make your double bond, use POCl3 and pyridine. See what I got now. Okay, now what if you have an alcohol and you want to end up with an alkane? Well, you cannot do it in one step. It's hard to do that. And so what they typically do is you take the alcohol and you go to the double bond. Okay, so what we just did, you make the double bond, and then you add, what's the difference between that and that? H2? H2 and a double bond, okay? So do you remember how to add H2 to a double bond? What do you need? You need a catalyst, okay? So don't forget to put your metal catalyst in. Platinum, nickel, rhodium, PTO2, palladium. There's like a bunch of them. You could probably almost guess an element off the periodic table and find a catalyst. That's how many there are. Well, I don't know about that. I don't know that you would, want to use chromium. Chromium's an oxidizing agent. So don't use that one. Okay? Okay, you can oxidize alkenes with OSO4. Remember that? The osmium tetroxide? Okay? And H2O2, and you make the little diols. Okay, how do the diols add? Remember syn? You make the syn diols. Okay. All right. So don't. Ooh. Gets exciting in here sometimes. Telling you. All right. Syn addition. Okay. So if you have cyclohexene, you're going to end up with the cis 1,2-cyclohexane dot. Okay. Notice that to show the cis. Okay. There's a wedge and there's a slash. If the wedge or the slash is for the hydrogen, you can draw it like this and it's assumed. So this would be the same thing as the one that's there. Okay. All right, but you can't have 3 flat. You can only at any time with a sp3 hybridized carbon have 2 bonds in the plane. Remember that from stereochemistry way back to the dark ages of last semester? Okay, you can only have 2 bonds and you can't have 3 flat. You only get 3 flat when you have a carbocation or an sp2 hybridized carbon. Okay, but with the sp3 hybridized carbon, you can't have 3 flat. That's why this is not correct. This is actually 4 flat. Okay, but if I did this, okay, you see why that really isn't correct, because you can't have 3 flat. This shows 3 in the plane, and you can't have 3 bonds in the plane. You take a tetrahedrocarbon and mess with it, you can't get it that way. You can only have 2 in the plane at a time, okay? So just quick remind you about that. Okay. Now, what then we do is we take those and we use periodic acid. Iodine is one of the elements that will break the octet rule as well. We don't run into it much except in this class, in this periodic acid. Okay? You get alkenes, or I'm sorry, from the alkene, you make the diol. From the diol, you then end up with ketones and or aldehydes, depending on what is connected to the carbons with the hydroxyl groups on. If you have 2 R groups, you get a ketone. If you have 1 R group and an H, you get an aldehyde. Okay, so here is a compound. They made this by doing this. And this was a 1E and a 2E. And we are going to have RC. CHR, right? Okay, so they're going to take that ketone and make it into the diol, and then they're going to add HiO4, and they're going to bust it apart. Okay, don't worry about those arrows. Okay, what you need to know is that it breaks, and you get a ketone and an aldehyde, depending on what was hooked to them. Notice your little byproduct is HiO3. All of a sudden the iodine lost an O, didn't it? Okay, and we get HiO3 off of that. All right, so what will you get from this one? Then we're going to do that little deal. How are we doing? Oh, we're doing good. Okay, so we're going to add HiO4 to that. So where are we going to break the molecule? We'll put a little squiggle. We're going to break the molecule between the 2 carbons that have what on them? Okay, so from this carbon up here, what are we going to get? A ketone. I kind of messed it up. I should have gone up. Okay, and then from this carbon here, the bottom carbon, we're going to get an aldehyde. Basically, you break it, you put carbonyls there. Okay, so here's what it looks like drawn much nicer. Okay. Follow? Okay. An alkene is treated with OSO4 followed by H2O2. When the resulting diol is treated with HiO4, the only product obtained is an unsubstituted cyclic ketone with the molecular formula C6H10O. What is the structure of the starting alkene? Okay, I got 1150. So you do that for class on Wednesday. Okay. Okie dokie. Okay.